Dear colleagues, greetings from the Czech Republic. I'm Pavel Porizka from CETEC, Brno University of Technology, and I'm going to present you benchmarking in laser-induced breakdown spectroscopy. First of all, let me apologize for not being there in Arizona with you and enjoying the conference. And second, let me thank to the organizers, especially Dr. Barnes, for giving me this opportunity so I'm able to present you our work in this way. In my presentation, I'm going to tell you more about contest that has been held in LIBS community and introduced, and in the second, I'm going to tell you more about benchmarking. It means large data sets that helps us to compare individual groups, approaches, and so on. I'm also going to tell you about the data set that we have developed, created, and made public for all the groups that are interested in chemometrics. We are also doing some chemometrics on our own, so I'm going to tell you a brief introduction about the way how you can analyze your samples and data. So first of all, LIBS contests. There are numerous contests already existing, and they have been introduced to the best of our knowledge in 2008 from the Federal Institute of Materials and Testing in Germany for the LIBS conference in 2008. It was a quantitative analysis of different analytes in steel. Very similar contest was also introduced for the LIBS 2016 held in Chamonix, France, where very similar metrics was analyzed, but the problem of measuring steel samples was introduced there, and it's something that gives another challenge to the LIBS groups. First of all, they have to do very robust analysis, meaning experimental, and then also doing very good data processing. Something similar was also introduced by the French group centered around Dr. Motoros. This work is also published. You can see the reference to this work. In this work, they have only shared data between different groups, and they were interested in the quantitative analysis. We have done something similar in our case for MSLIBS 2019, held last year, just a few months ago. And we have so far very interesting results that we are going to also publish. And this data set is still available, so you can still work on it. So here you can see also the website of our contest, which you can access. You can download the data and you can still work on it, but you have to be also quite careful about the way how you process the data, because it's quite challenging. And that was the point, that we wanted to do another step forward in the size of the data set itself, also number of samples, and this is also called somehow the benchmarking. Benchmarking is a term in data science, and it means simply that there is some sort of data set, as in our case the LIBS contest data set, which is introduced, and it's a platform for the other groups to compare their approaches in data processing, in creating a model, creating generalized model, and so on. And this is also a way how to move forward the knowledge and expertise in laser spectroscopy. So for us, this is a sort of benchmark data set that still stands, and you are able to continue to participate, continue with this analysis, and trying to beat this benchmark as well. So for us, there is a clear motivation. We wanted to create a data set that is sort of bigger than what is usually seen in literature. In literature, you can find very limited data sets in terms of number of spectra per sample and also number of samples themselves. So you can see data sets that have 10, 20 maximum samples, And on those data sets, the researchers are doing some sort of geometric analysis. Of course, when you are trying to create a robust model, you have to have also vast data set where those samples and spectra are really challenging to be classified. So this is also the case of our data set, where we have several high number of samples, up to 140 samples, but those samples are not just created randomly, but they are also sort of blurred together, so they are overlapping in composition and so on. So there is a challenge in classification. Okay, so what you can see right now on this slide, there are two different data sets. First is a sort of common data set, common approach, where you have some bunch of samples, and for modeling and training, you are just picking few spectra of each sample and creating a model. But in our sort of, what we say, modern approach, you are just selecting few samples, all of their spectra, to create a model. And this is quite different way, because in our case, those data that you are then using for testing have not been seen by the model, and they are completely unknown to it. Unlike in the common approach, those spectra that are used for modeling and then for testing are very similar, and then the challenge in classification is just simply being put aside. So this is the way how you can also separate data, and our approach is simply demanding for a researcher, for a data scientist, to create more robust and generalized model in order to classify completely unknown spectra that has been introduced afterwards to the model. Okay, for us, we have a bunch of samples, we have quite a lot of experience in classification, and we have used many times OREAS certified soil standards, and we have just pressed them into pellets or created some sort of our own samples, our own certified samples, by mixing and so on. So in the beginning we had 46 unique materials, and we mixed them into 138 physical samples. There were several classes to which one has to classify them, and the point is that those samples are very similar in elemental composition. Why we were doing this mixing of samples? It's very simple, because we wanted to increase the challenge, in the sense that those spectra that are then analyzed are just very similar on the boundaries between two classes. What you can see also on the slide, on the left side, there are quite distinct clusters of samples, and this is something that is quite easy to classify. This makes no challenge, but when we are doing some sort of mixing, when we are just putting samples from different classes together, just very slight mixture, then it's something that is on the other side, where you see the blurred clusters, some clouds of data that are just mixed and joined together, and then doing some classification in there. This is the real problem, actually. Is really challenging, and as you have to work harder to get some robust and reliable classification. So we have the samples, and we also analyzed everything in-house using our system, where you can see some parameters of the energy, gate delay, gate width, and other parameters. So we have actually thousands of spectra per sample, but for for this contest we didn't show everything. You can see that we have 138 samples, 12 classes, 500 spectra per sample in training data set, and also everything was measured using an S-shell spectrometer, so we have 40,000 wavelengths, meaning huge dimension of variables in the spectrum. So those data are prepared for you to download and to work on, and you can see that the training has more than 7 gigabytes of data and the test has 3 gigabytes. But this is just only a fraction of the total data set that we have collected, and soon we are going to publish all of the 5,000 spectra per sample, so you can work on everything that we have. At the moment, and for the contest, there are only 500 spectra. We have also import scripts, so you can work in Python, MATLAB and CRAN packages, so there is only your decision to make which software you would like to use. So also there is another motivation for us to do such a contest, is that recently a lot of scientists are just classifying spectroscopic data without having some spectroscopic insight on the data. They are just applying hardcore or just more complex data processing algorithms without doing some real spectroscopic work, looking through the spectra, qualitatively analyzing different spectral features. And when you have low number of samples, it can give you still good results. So that was the idea of also doing this data contest. And the question is pure data approach enough? Just using hardcore algorithms such as neural networks on bunch of samples, it will work somehow, without even just using a black box approach. But in this case, when you have quite complicated data structure and a lot of data and samples to classify, it's really a challenge also for neural networks to do some reliable classification, accurate classification. So you can see, very simple example, taking raw spectra, creating a model with neural networks, having parameters, as you can see, 3 layers, and in the end we arrived to have only 70, or to receive only 75% accuracy. So you can see that you can also use very advanced algorithms such as neural network, but you are receiving only very low performance in terms of accuracy. So it means that pure data approach is simply not enough. And you have to improve, you have to work on the data to connect it with the background, with physics, chemistry, and the spectroscopy itself. So it's very necessary to understand the data. It's the way how you can increase the accuracy and improve your data processing. So in this presentation, I'm not going to give detailed way how to process all the data and how to reach very high accuracy. I'm going to give you some hints to guide you and show you the way how to start, because I would like to also you to join our contest and try it on your own. So first thing is to just do some visualization of obtained data, do some principal component analysis, coherent maps, then doing some dimensionality reduction and outliers filtering to really reduce the data set in terms of variables, maybe also in objects, meaning spectra, and then do some iterative improvement of the model and its generalization. This means that you can repeatedly upload your results to our database and see in real time the feedback, giving you the accuracy with which you have classified your data. There is also some inspiration in review articles from José El-Haddad and also from our group. Both of them were published in Spectrochemica Acta. They give some overall review and know-how on data processing using chemometrics in laser-induced breakdown spectroscopy. We are almost at the end of our presentation. I would like to show you also, because this contest itself was already closed, finished, and we are going to publish the best 5 approaches that reached more than 90% of our winner, Ludovic Duponchon and his team from France, reached more than 90% of accuracy. There are also other very good results from the German groups and other participants. So you can see there is the column called accuracy, giving you iterative improvement of their model. So you can repeatedly upload your results and see how your model is improving. You have to be careful about the point that you are overtraining your data and then you are getting biased results. So this is really to validate your model. And then in the end there is another column, one-shot test. It means you can upload, we have opened new data, you can take them, process them in your approach, and then you can see what is if your approach and model is really robust or not. Then you can give this one-shot test and see that in the case of German groups, their models and ways of data processing is really robust and is really good. We are going to publish those approaches in Spectrochemica Acta in hopefully as soon as possible. It will be virtual special issue of MSLIBS 2019. At this point I would like to highlight the website of our contest. Once again, I would like to acknowledge the work of my co-authors, especially Jakub Rábel and Erik Képes, and also our funding. And thank you for your attention.